Okay, this is the third part of the final exam review, which deals essentially with phase changes, ice, water, and steam. And so let's just go through this again. Just before the liquid working fluid in an air conditioner enters the evaporator, it flows through a constriction that dramatically lowers its pressure. The low pressure liquid enters a gas-filled chamber where the liquid evaporates into a gas. Lowering the pressure of the liquid encourages it to evaporate into a gas because low pressure liquid is more gas-like than high pressure liquid. Low pressure gas has pressure potential energy than high pressure gas. 3. The rate at which molecules land from the gas on the surface is greatly reduced. And 4. Low pressure liquid has a higher temperature than high pressure liquid. It's this one. And again, the idea is that when you have liquid and vapor in equilibrium, then essentially if you have a cup of water, then what you have is essentially water molecules that are in the atmosphere. And you're constantly taking water molecules going out into the atmosphere, and occasionally they come back down. And if you have a thermal equilibrium, then essentially the amount of water vapor in the atmosphere and in the water basically stays constant. So if you're at 100% relative humidity, it just always stays constant. On the other hand, if you pump out the vapor, and so basically you have a vacuum, you have many fewer water vapor molecules up here, and so on average the water molecules tend to jump up and they're not balanced by water molecules coming back. And so as a result, what happens is that you'll greatly increase the reduction of the vaporization of the water. Essentially it will evaporate very rapidly. In fact, you can boil things at room temperature if you have a vacuum on top of it. You're fond of boiled eggs, which you normally cook for 3 minutes while in Cincinnati. You're taking a semester abroad, however, and living at 15,000 feet in the Andes Mountains of Chile. You put an egg in a pot of boiling water and wait 3 minutes. Sadly, the egg turns out badly undercooked because the reduced atmospheric pressure in the mountains causes the hot air bubbles in boiling water to expand too quickly and rise out of the water before they have a chance to heat the egg. 2. Reduces the density of air bubbles inside the boiling water so the hot bubbles do not undergo convection well and cannot heat the egg quickly enough. 3. Allows bubbles of pure steam to exist and grow inside the water at a temperature below 100 degrees C or 212 degrees Fahrenheit. Reduces the density of air bubbles inside the boiling water so the bubbles do not conduct heat well. What happens is as the density, as we just talked about, is if you lower the vapor density, then what happens is it allows essentially bubbles to form at much lower temperatures, and so the boiling temperatures can get very, very low. And so it's difficult to cook things. In fact, it can be kind of unsafe because you can't kill bacteria. On the other hand, if you increase the pressure, so it's above atmospheric pressure, you can actually increase the boiling temperature significantly, which is why they use pressure cookers to sterilize instruments in hospitals. Third one. It's a bitter cold winter morning and there are thin patches of ice on your sidewalks. Although the temperature never rises above 10 degrees Fahrenheit, minus 12 C, the ice is gone when you return in the evening. If you'd examined the surface of the ice closely enough, you would observe water molecules only leaving the solid for gas, leaving the solid for the gas much more often than they land in the gas from the solid. 3. Becoming separate oxygen and hydrogen molecules and entering the gas phase. 4. Leaving the solid for the gas much less often than they land on the gas from the solid. So what happens is that they leave for the solid for the gas much more often than they land from the gas to the solid. What you get is this is what happens with sublimation. It basically goes directly from a solid to a gas. You basically need both the latent heats of fusion, which goes to water, and also the latent heat of vaporization. And so it needs all of that energy basically to remove them, but they go directly into gas phase and not into liquid. And so it sublimates. When you leave dry ice, solid carbon dioxide on the kitchen counter, it gradually disappears without ever becoming a liquid. If you were to examine the surface of the dry ice closely, you'd find the carbon dioxide molecules, 1. Leave the solid for the gas much less often than they return from the gas to the solid. 2. Vibrate exponentially and oscillate into dust. 3. Leave the solid for the gas much more often than they return from the gas to a solid. 4. Become water molecules as they warm up and dissolve the humidity. And remember, This again is looking at this equilibrium, and so if it leaves the solid much more rapidly, more often than it comes back, then basically it sublimates it. You gradually get less and less and less. So it leaves the solid for the gas much more often than they return from the gas to the solid. Just there. Okay. 5. You're drinking a cup of hot coffee in an airplane at 35,000 feet. Suddenly the airplane pressurization system fails and the cabin's air pressure decreases abruptly. The coffee begins to boil because its temperature, 1, has suddenly decreased, 2, hasn't changed, but bubbles of pure steam are now stable inside it. 3, has suddenly increased. 4, hasn't changed, the temperature hasn't changed, but the air bubbles inside it have suddenly expanded. The temperature doesn't really change very much, at least initially, but bubbles of pure steam are now stable inside it. Because the vapor pressure is, again, low, it changes this equilibrium, and so what happens is that you can form steam bubbles inside the liquid much more readily. So you can boil things at even room temperature. You and a friend are at a restaurant. Each of you has a glass of ice water. Your glass contains 75%, 25% water, while your friend's glass contains 25% ice and 75% water. The temperature of water in your glass is higher than the water of your friend's glass, the same as the water of your friend's glass, 0 in absolute temperature scale, lower than the water in your friend's glass. You've got more ice, but as long as you've got ice and water in equilibrium, they're exactly the same temperature. It's 0 degrees C or 32 degrees Fahrenheit. So it's the same. If you put salt into water, the boiling point of water rises and the freezing point of water falls. The boiling point of water falls and the freezing point of water rises. The boiling point of water rises and the freezing point of water rises. 4, the boiling point of water falls and the freezing point of water falls. So when you put salt into water, what happens is that's how you melt ice on the roads. And so the freezing point of water falls, and so it might actually only melt at basically 0 degrees Fahrenheit. And whereas the boiling point rises. And this is essentially because the salt, because it's essentially an ionic solid, sodium plus and chlorine minus items, and the water is essentially very polarizable. The oxygen carries sort of negative charges and the hydrogens carry positive charges. Is that putting salt into the water basically stabilizes the water phase, which makes it harder to freeze and also harder to boil. So the boiling point rises and the freezing point of water falls. Last one. Beach use is used to treat the roads before a snow or ice storm because sugar causes the melting point of ice to be lower than 32 degrees Fahrenheit. Sugar causes the melting point of ice to be higher than 32 degrees Fahrenheit. 3, sugar causes the roads to be stickier, increasing the traction of the tires. 4, as sugar oxidizes in the air, it warms the road and melts the ice. And essentially sugars, these which basically is fructose, acts exactly like sodium chloride in that you get these ionic charged solids. And when it goes into solution in the water, it tends to stabilize the water, and so it reduces the freezing point of water below 32 degrees Fahrenheit. And so on. So that ends this discussion. And that basically ends the material that we covered in the second half of the course. And so kind of you can view the midterm review because that's still online. And so you should be able to see that. At least there's an audio for it. It always seems something happens for the reviews. I don't know why that happened in midterm and also for the final. I may be able to get to the earlier stuff, but I haven't yet been able to get to it yet. So anyway, hopefully this helps you study for your final exam. Good luck this week, and I'm sorry things got so messed up because of the power outage this morning. So anyway, I'll be in email contact. I'll be in Portland, but I will be in email contact all next week. And so if you have problems with the final exam, please don't hesitate to email me, and I'll do the best I can to try to take care of problems. Please don't wait till the end of the week. Thanks a lot.